Today, lasers are everywhere. There are medical lasers to correct vision, lasers at the checkout counter, lasers for cutting, communicating, entertaining cats, and of course, for light shows, which encourage us all to trip the light fantastic. Which may be why experimental physicist Rana Athikari is laser-focused on lasers.
When I talk about how beautiful a laser is as an instrument, I don't want to gush about it too much, like I'm in love with lasers, I don't know. I feel like a weirdo fanatic or something like that, but there's something about them.
To understand what makes laser light so special, it makes sense to look at an ordinary light bulb, the old-fashioned kind, with a tungsten filament. It produces light through thermal radiation. An electric current passing through the filament heats it up. Its tungsten atoms become excited and vibrate at different speeds, which causes them to emit photons in all directions across a variety of wavelengths. Compared to a laser, this is chaos.
And the way you should think about a light bulb is something like they're just a mob of people all singing a different pitch, so it's like a rock concert audience. But a laser is more like if you go to Juilliard or Berkeley School of Music and you go to a concert, it's like a choir of people who have got perfect pitch. But it's a choir of something like 1,000,000 trillion people singing at the same time, the same tone.
That's because laser light is generated in an entirely different way. A fact hidden in its name, stimulated emission.
Let's say we have inside an atom an electron that's at some excited state, some higher energy level, and now a photon of just the right frequency passes by the atom. It triggers the atom to do something interesting. The electron loses energy and goes to a lower energy and emits a photon of precisely the same frequency as the one that came in. It's going in the same direction and it has the same phase. So what we have there is a quantum mechanical amplification process.
If we place a group of those same excited atoms inside a chamber with mirrors at both ends, the emitted photons will bounce back and forth, continuing to stimulate the emission of more photons, which in turn stimulate even more photons. One of the mirrors is only partially reflective. It allows some of the light to escape.
Now that light's very special. It's composed of photons that are all the same frequency, so the same color, and they're all the same phase and all going in the same direction. So you have this intense, pure beam of light, and that's the laser.
Lasers have proven to be an extremely versatile tool, including for measuring distance. Rana's work with stable high-frequency lasers takes that to an extreme.
When you use them, you're in a whole different realm of measurement than anything else that has to do with rulers and any of that other stuff. Anybody who's like a real pro knows that the only thing that you ever measure is frequency. If you measure anything else, you're kind of an amateur.
Thanks to the fixed speed of light, the beam of a high-frequency laser has an incredibly short wavelength, perfect for measuring extremely small changes in distance. Since 1996, Rana has been part of a project that uses laser light to measure something incredibly, unimaginably small and weird. tiny fluctuations in the fabric of space and time itself.
Space and time ripple. They're not fixed things. And so the distance between my two hands is not always going to be this if I hold them steady.
The idea, like so many, goes back to Einstein. In the early 20th century, his work led to the merging of space and time into one concept, space-time. And he theorized that gravity was the warping of that space-time fabric by the mass of objects. But that carried a startling implication: that the acceleration of objects with mass would create ripples in space-time that spread at the speed of light, gravitational waves.
Gravitational waves were first predicted by Einstein, and he didn't believe it at first, so he went back and forth through, I believe, the mid-30s. But his first prediction was they were too minute to ever be detected.
By the 1980s, that sentiment had changed, and LIGO, the Laser Interferometer Gravitational Wave Observatory, was founded as a joint Caltech and MIT project. Part of Rana's work at Caltech has been to continuously improve the essential art of LIGO, laser interferometry.
This is where it all begins. I'm going to show you the whole laser interferometer in here. That's a prototype of the LIGO system.
The basic design is easy to understand. The LIGO interferometer has two arms at right angles to each other. A very stable infrared laser feeds into a beam splitter, which directs half the beam down each arm.
Half of the light goes one way and half goes the other way. And then you have mirrors at the ends, and they reflect the light back.
The phase of one arm of the laser is the reverse of the other. If all is normal, when recombined, they will cancel each other out, resulting in no signal. But if a gravitational wave passes through, distorting space-time, the length of each arm will change, shifting the phase of the two beams. For a brief moment, the equipment will register a signal.
Instead of having exact cancellation and destructive interference, you have a little bit of light leaking out. And that little bit of light that leaks out is what we detect.
But there is a key difference between Rana's working test bed and the real deal: size. This is one of two LIGO installations in the United States. While the arms of the Caltech instrument are about 44 yards long, the ones here cover about 2.5 miles each. Costing hundreds of millions of dollars, LIGO was a huge gamble on an unproven idea that paid off. In 2015, a signal was detected. And it was a doozy.
The first event that LIGO detected was the most powerful event human beings had recorded since the Big Bang itself. More power came out of that collision of those two black holes than was emanated by all the stars in the universe combined. All of that power came out in the ringing of the drum of space-time.
Since the original event, LIGO has confirmed the detection of more than 80 others. It is hard to overstate the significance of the discovery.
LIGO is massive. Albert Einstein predicted that gravitational waves should exist, and now we measure them. This is the most direct observation of black holes that we've ever had. This is a complete revolution in science.
And it's all possible because of that quantum technology that has become completely embedded in our lives: the laser.
The more stable your laser is, the more things in the universe you can measure, and there's no limit to it. So Every year when we get lasers better and better, we'll be able to see further out into the universe and see tinier things in the microscopic nature of reality, matter, space and time, anything like that. You just have to keep working on this one tool and make it better and better.
Arguably, the most important change in quantum physics in recent decades is a deeper understanding of a special kind of shared state called quantum entanglement. Imagine a machine that spits out pairs of coins, which on the surface look like ordinary coins. If you flip one, it comes up heads or tails, about 50% of the time. Nothing strange there. But using a pair of coins fresh out of the machine, you flip one, it comes up heads. And then the other, it also comes up heads. That could just be luck. So then you do the same thing with another fresh pair. This time the first coin is tails, and so is the second. Agreement again. So you flip another pair, and then another, and another, and another. Pair after pair, the two coins always agree on the first flip. What's going on? Maybe the first flipped coin, once it comes up heads or tails, is somehow telling the other coin how to behave. To make sure that can't happen, you separate the coins by flying one to the moon and flip them at the same time, so no message could possibly travel between them. Still, they come up in agreement. It all sounds too strange to be true, but particles really can behave like those coins. In quantum physics, it's called entanglement.
Entanglement is really just this stubborn, exciting and/or frustrating fact that takes a long time to try to get our heads around.
Entanglement is certainly the most interesting and the most confusing aspect of quantum.
It's one of these things we don't see, naively in the world around us, but it is taking place deep in the materials that exist around us every day.
And while you probably won't come across a coin entangler anytime soon, in the lab, scientists routinely generate pairs of entangled particles that share a quantum state so fully they can be thought of as one quantum object.
You simply can't differentiate between them. It's just one pure state.
It's as though you have a single entity that's spatially separated without a physical connection.
Entangled particles remain connected even when they're separated by hundreds of miles, and likely far more.
So does that mean it can go between here and Andromeda? Probably. The equations give us no reason to think it wouldn't.
Entanglement sounds bizarre. Einstein derided the idea as spooky action at a distance. But since the 1970s, experiment after experiment has confirmed entanglement is a real quantum phenomenon.